Hi everyone, welcome to Unit 8 of online course on probability distribution. In this session, we are going to discuss the concept of mode and recurrence relation of binomial probabilities and some examples. As you all know, for a discrete random variable, mode is obtained by identifying the value of the random variable by which the probability mass function is maximum. So, to find the mode of the binomial distribution, we consider the binomial probability mass function and find which value of x make that probability mass function as a maximum. So, for a discrete probability distribution, the value x at which the probability mass function takes its maximum is known as the mode of the distribution. And for the binomial random variable with the parameters n and p, if x is the mode of the random variable, then mode is obtained by this relationship np plus p minus 1 This is the way we are obtaining the value of the mode of the binomial distribution. So, that is, suppose x is a binomial random variable with the parameters n and p, and we know the probability mass function f of x is equal to NCX p power x q power n minus x, where x is equal to 0, 1, 2 up to n and p plus q is equal to 1. This is the probability mass function of the binomial random variable. Our aim is to obtain the mode of the distribution. As I mentioned, the mode of the discrete random variable is obtained in such a way that you identify the value of the random variable by which the probability mass function, this f of x, is maximum. That is, f of x is, suppose x is the mode of the distribution, then f of x is maximum. That means, f of x is greater or equal to all other f of x values less than x value. That is, x is equal to 1, 2, 3, etc. up to n. And f of x is greater than or equal to f of x plus 1. So, you identify these two inequalities, f of x greater or equal to f of x minus 1, and from this you derive certain inequality, and again f of x greater or equal to f of x plus 1. From that you derive another inequality. You combine these two inequalities, you will get the concept of, or you will get the value of the mode of the distribution. And to get the mode, what we are doing here, you simplify this f of x greater or equal to f of x minus 1. That is, NCX p power x q power n minus x greater or equal to NCX minus 1 p power x minus 1 q power n minus x minus 1. So, when you substitute the values of f of x and f of x minus 1, this is the inequality. And that is, you simplify this fact this can be written as n factorial divided by n minus x factorial into x factorial p power x q power n minus x greater or equal to n factorial divided by n minus x minus 1 factorial into x minus 1 factorial into p power x minus 1 into q power n minus x plus 1. Let it be like this. So, that is, see, this n factorial common factors can be cancelled, and from this x factorial and x minus 1 factorial, so x is remaining there, and this n minus x factorial and n minus x minus 1 factorial, you make it as, so that is our simplified expression become, this is the value. So, that means when we have the, this is equal, this is simplifying, we will get this 1 n minus x into this p is here, and this is greater or equal to q divided by n minus x plus 1. Sorry. So, this is the remaining factors. So, that is, we have p by x greater or equal to q divided by n minus x minus 1. This is our expression. So, p by x greater or equal to q divided by n minus x minus 1, simplifying, we have x less than or equal to n p plus p. So, that means you start from f of x greater or equal to f of x minus 1, you substitute f of x and f of x minus 1, simplifying, finally, you will get the inequality like this, x less than or equal to n p plus p. Similarly, you find the second case, that is f of x greater or equal to f of x plus 1. When you have f of x greater or equal to f of x plus 1, we have already we have the value of f of x n c x p power x q power n minus x greater or equal to n c x plus 1 p power x plus 1 q power n minus x minus 1. And as in the previous case, here also you just write this n factorial divided by n minus x factorial p power x q power n minus x greater or equal to, this is n factorial divided by n minus x plus 1 factorial into x plus 1 factorial p power x plus 1 q power n minus x minus 1. So, this is the expression, and from this common factors are cancelled, this reduces to, this is p power, this n factor will be cancelled, and from here p power x and p power x plus 1. So, 1 p is remaining the right side. So, this is p, and x plus 1 factorial and x factorial, you consider x plus 1 remaining here, and n minus x factorial and n minus x plus 1 factorial, this n minus x is remaining here, and q power n minus x and q power n minus x minus 1 common factor cancelling, q is remaining. So, when we have the expression of f of x and f of x plus 1 and simplifying, that is cancelling the common factors from the left side and right side, finally you have the expression q divided by n minus x greater or equal to p divided by x plus 1. And this is cross multiplying, you have this actually this q into x plus 1 greater than or equal to p into n minus x, or that is qx plus q greater than or equal to np minus xp. And that is this qx, and this factor is taken this here. So, qx plus xp greater than or equal to np minus q, and qx plus xp means q plus p into x is greater than or equal to np minus 1 minus p. Q is our 1 minus p. That is q plus p is equal to 1, you know. So, that is this side become x. So, this is x greater than or equal to np minus 1 minus p or np plus p minus 1. So, earlier we have the expression as this is x greater than or equal to the earlier we have the expression x is less than or equal to np plus p. In the first case we established this result, and now we establish this result. Combining these two inequalities, we have np plus p minus 1 less than or equal to x less than or equal to np plus p. So, that means for a binomial random variable, suppose we are finding the mode of the random variable, mode of the distribution, that means the value of the random variable by which the probability mass function is maximum, that is obtained by identifying the value of x in such a way that x lies in between np plus p minus 1 less than or equal to x less than or equal to np plus p. So, this is the concept behind finding the value of the mode of the distribution. But remember that this np plus p minus 1 less than or equal to x less than or equal to np plus p means it is not possible to take all possible values from np plus p minus 1 to np plus p as the mode of the value, because you know x is a binomial random variable. It is a binomial random variable. So, that means it can have the values only like this 0, 1, 2 etcetera up to n. So, that is np plus p minus 1 less than or equal to x less than or equal to np plus p. Any value x satisfying this two expressions, this np plus p minus 1 and np plus p, you identify the integral values, and that integral value is the mode of the distribution. So, once again I repeat, since x is a binomial random variable that can have only integral values 0, 1, 2, 3 etcetera. So, first of all you find np plus p minus 1 and np plus p, and in between this np plus p minus 1 and np plus p you identify the integral value, that is it may be 0 or it may be 1 or 2, 3 etcetera, and that value is our mode of the distribution. And to convince this concept, I will give one example here. Find the mode of the distribution x follows binomial with 4 and 1 by 3. So, that is one example. X is a binomial with a parameter 4 and 1 by 3. We derived the mode of the distribution always satisfying this. So, if x is the mode, we have this. This is already we proved. If x is a mode of the distribution, that x satisfying this criteria. And here what is np plus p? Np plus p here is 4 into 1 by 3 plus 1 by 3. That is 4 by 3 plus, so 5 by 3. So, np plus p is equal to 5 by 3. Similarly, you find what is np plus p minus 1. of course, that is equal to the 5 by 3 minus 1, that is 4 by 3. Sorry. So, this is N p plus p is already we calculated as 5 by 3 minus 1, that is 2 by 3. So, that is our N p plus p minus 1. So, that means see, this is 5 by 3 and this is 2 by 3. So, that is the thing. So, in between 1 by 2 by 3 and 5 by 3, you find which is the value of the mod. The mod is equal to, say it is 2 by 3 and this is 1 by 5 by 3 means it is the only value is here is 1, 1. So, for this particular random variable, the mod of the distribution is equal to 1, because in between 2 by 3 and 5 by 3, the only integral value is equal to 1. So, mod of the distribution is equal to 1. Similarly, for the second example, binomial with n is here 7 and p is equal to 1 by 4. Here also you find what is n p plus p. N p plus p means 7 into 1 by 4 plus 1 by 4. So, that is 8 by 4, that is 2. So, N p plus p is 2 and N p plus p minus 1 is equal to 2 minus 1, that is equal to 1. So, mod of the distribution N p plus p minus 1 less than or equal to x less than or equal to N p plus p implies 1 less than or equal to x less than or equal to 2. So, mod of the distribution, mod of that binomial distribution is in between 1 and 2. And in between 1 and 2, both 1 and 2 are included. There are two integral values, x is equal to 1 and x is equal to 2. So, for this particular random variable, mod is equal to 1 and 2. That means, for that particular distribution mod, there are two modes. That is, this is an example for a bimodal distribution, because binomial random variable with 7 and 1 by 4 have the mod at x is equal to 1 and at x is equal to 2. So, these are the ways, these are the some examples by which we are identifying the mod of the binomial distribution. And another example, find the mod of the binomial distribution for which mean is 4 and variance is equal to 3. This is an indirect question. Suppose you are given that a binomial distribution is given to you and mean is equal to NP is equal to 4 and variance, that is equal to 3. So, this is given to you. For the binomial distribution, mean is equal to 4 and variance is equal to 3. That means, NP is equal to 4 and NPQ is equal to 3, or that is NPQ divided by NP is 3 by 4, or that implies our Q is equal to 3 by 4. That implies P is equal to 1 by 4. Hence, what is N? NP, see NP means N into 1 by 4 is equal to 4. That implies N is equal to 16. So, actually the parameters are not specifically given, but given the mean and variance of the distribution. Using the mean and variance expression, you are solving the quantities, solving for the values of the parameters N and P. We have the value of P is equal to 1 by 4, N is equal to 16. So, that is n is equal to 16, p is equal to 1 by 4, you find np plus p minus p first. Np plus p means 16 into 1 4 plus 1 by 4. So, that means 4 plus 1 by 4. And so, np plus p minus 1 here 3 plus 1 by 4. So, for this particular distribution, mod is 3 plus 1 by 4 less than or equal to x less than or equal to 4 plus 1 by 4. So, this is the property of the mod, that is for the binomial distribution for which mean is equal to 4 and variance is equal to 3. First of all, we find the parameters n and p here, that is by solving the equation n p is equal to 4 and variance n p q is equal to 3. Solving, you have the value of q is equal to 3 by 4 or p is equal to 1 by 4. And substituting that p value in any of the equations, this the first equation n p is equal to 4, that gives n is equal to 16. So, for the binomial distribution, the parameters are 16 and 1 by 4, and from that you find the mod of the distribution. But the mod is obtained by identifying the value of np plus p and np plus p minus 1. Np plus p is equal to 16 into 1 by 4 plus 1 by 4. 16 divided by 16 into 1 by 4 means 4 plus 1 by 4, and np plus 1 p minus 1, that is again 3 plus 1 by 4. So, mod is 3 plus 1 by 4 less than or equal to x less than or equal to 4 plus 1 by 4. What is the meaning? In between 3 plus 1 by 4 and 4 plus 1 by 4, there exists only one integral value, for that is our x is equal to 4. So, for this binomial distribution, mod is equal to 4. So, this is the way in which we are deriving the mod of the distribution if the parameters are not specifically given, but given in terms of some other values, that is mean is equal to 4 and variance is equal to 3. Like this, we can do any problem of this type, that is suppose you are given the mean, variance, moment generative function, etc. How you can find the other quantities related with the distribution, that we will discuss in the next units. Before that, let me introduce this recurrence relation also here. Recurrence relation for binomial probabilities, that is f of x is our probability mass function. Suppose x is a binomial random variable, f of x is our, this is actually probability of x is equal to x is our probability mass function, that is our f of x. So, this is f of x is n c x p power x q power n minus x. Now, we are deriving a recurrence relation between the binomial probabilities. How do you find the binomial probability values if one of the probability value is known to you? That is, this is the formula, f of x plus 1 is equal to n minus x divided by x plus 1 into p by q f of x, where x is equal to 0, 1, 2, 3, etc. This formula provides us a very convenient method of finding binomial probabilities corresponding to x is equal to 1, 2, 3, etc. And the only probability value we require to calculate this probability values corresponding to x is equal to 1, x is equal to 2, x is equal to 3, etc. is f of 0, the first value, that is f of 0. And of course, f of 0, that is our probability of x is equal to 0, is equal to q power n. So, if q power n is known to you for a binomial random variable, if q power n is known to you, without going to calculate other binomial probabilities using the usual expression, it is possible to find the binomial probabilities using the recurrence relation f of x plus 1 is equal to n minus x divided by x plus 1 into p by q f of x. The derivation of this formula is very simple, just to consider the value of the f of x and f of x plus 1 and that will give us the. So, this is this NCX p power x, this is, you can prove this by just consider this this f of x NCX p power x q power n minus x, and suppose I am finding f of x plus 1 here, NCX plus 1 p power x plus 1 q power n minus x, then this implies, suppose you are finding f of x plus 1 divided by f of x, this is equal to NCX plus 1 divided by NCX and then p power x plus 1 divided by p power x q power n minus x plus 1, sorry, this is q power n minus x. So, substituting f of x plus 1 and f of x like this, and from this the common factors are cancelling. So, and NCX plus 1 and NCX is simplifying, you will get the result on simplification, you will get f of x plus 1 is equal to n minus x divided by x plus 1 p by q f x. So, the way in which we are establishing the recurrence relationship, just substituting the f of x value and simplifying, the common factors are cancelling, you will get the result. And what is the advantage of this formula? And in order to understand the advantage of this formula, let me give one example here. Suppose you are tossing a coin 7 times, for an experiment of tossing 7 coins is repeated 128 times, suppose, and the following distribution is obtained. That is, you consider experiment of tossing 7 coins and that is repeated 128 times. And how many experiments there are 0 heads, and there are when 8 coins are tossed, the possibility of getting heads, it may be 0, 1, 2, etc. up to 8, sorry, 7 coins, sorry. 7 coins are tossed here, and so seven coins are tossed, and so there may be 0 head, 1 head, 2 heads, etc. up to 7 heads, and this experiment is repeated 128 times. And out of this 128 experiments, you classify the experiments in which there are 0 heads, there are 1 head, 2 heads, 3 heads, etc. up to 7 heads. And suppose this is given to you. This is the observed number of frequencies, that is 0 heads, 7 experiments, 1 head, 6, 2 heads, 19, up to this. The total become 128 times. This is 128. And how do you find the expected frequencies? If this is an experiment and this is an experiment satisfying binomial distribution properties, because there are 2 possibilities, success and failure, coin is tossing either head or tail, and probability of getting success, that is probability of getting head, is 1 by 2. You can consider this as a Bernoulli sequence, and if it is so, using the binomial probability mass function, you can find the binomial values, probability values. On the basis of probability values, you multiply the total number of experiments, you will get the expected number of experiments in which 0 head is obtained, in which 1 head is obtained, in which 2 heads are obtained, etc. So, here you are finding, first upon you are finding, so you are given n is equal to 7 and p is equal to 1 by 2 is the parameters of the distribution, and f of 0 you are finding, and you know f of 0 is, our f of 0 is nothing but probability of x is equal to 0, and by binomial probability this is nc0 p power 0 q power n minus 0, or that is equal to q power n. So, this is q power n, f of 0 is q power n, and that is q is equal to 1 by 2. So, 1 by 2 power 7, that is 1 divided by 128, and total number of trials or total time the experiment is repeated 128 times. So, if it is, how do you find the other binomial probabilities? We obtain the first probability f of 0, and using the recurrence relationship you can find other binomial probabilities, that is use the recurrence relation f of x plus 1 n minus x divided by x plus 1 p by q f of x, that we established earlier, recurrence relationship between the binomial probabilities. And so, f of what is x is when x is equal to 1, we have f of 1 is equal to n p divided by 1 into q f of 0. Since already we have established that f of 0, that is our q power n, that is our 1 by 2 power 7, that is 1 divided by 128. So, this is f of 1 is equal to n p divided by 1 into q f of 0, that is n is 7 into 1 by 28. Similarly, f of 2 using the recurrence relation, this is n minus 1 divided by 2 p by q f of 1. Already we have f of 1 is 7 into 1 by 2, 7 into 1 divided by 128. So, this value is obtained. Like this, you can calculate f3, f4, f5, f6, f7. So, instead of going for calculating f1, f2, f3, f4 using the usual formula ncx p power x q power n minus x, using the recurrence relationship we are calculating the values f1, f2, etc. And so, these are the values f3, f4, f5 are obtained like this, f6 and so if you are considering a tossing of 7 coins at a time, simultaneously you are tossing 7 coins, and that experiment is repeated 128 times, and the observed frequency is given to you. Observed frequencies are, these are the observed frequencies, and suppose you are finding the expected frequencies if the distribution is binomial, if we are using the binomial distribution there, you can find the expected frequencies, and expected frequencies are obtained by the corresponding probability values are multiplied by capital N is equal to 128. So, earlier we have the value f of 1 we have calculated, sorry f of 0 we have calculated 1 divided by 128. So, this value is 1 divided by 128 is our f of 0. Suppose we have f of x values are calculating, this is the, so this is 128 into 128, this is 1, and we have 128 into 7 into 128, 1 divided by 128 is our value. So, that is our 7, and we have 128 21 into 1 divided by 128 is the value. So, we have 21. Like this, these are the expected values of the expected frequencies when you are tossing 7 coins simultaneously and repeating the experiment 128. So, this is obtained by using the application of the recurrence formula. Even though if we are not using the recurrence formula, you can find these values directly using the binomial probability mass function formula, but using this recurrence relationship is more convenient to get the values. So, with this we wind up this session here, and we will further discuss applications of binomial distributions in the next session. Thank you for listening this session. Thank you.